be speaking on traces of cycle integrals of meromorphic modular forms and coefficients of harmonic Maass forms.
Yeah,
Please.
thanks very much for having me. Apologies for the long title you have to read out. Yeah, so this is a great place to talk about our work. Thanks to the organizers for organizing this. So I spoke last time as well, and this is a fantastic way to meet up with everyone over the pandemic. So first I should mention this is all joint work with Claudia Alfers-Neumann, Katrin Bringmann, and Markus Schwalenscheid. There are some scary words in this title, but I'll explain everything as we go. I also apologize in advance. There is some technical notation that we need to show off the theorem, but I'll try and explain everything in more or less okay terms as we go. Okay, so let's start with just a little bit of the importance of cycle integrals and their traces. Where do they show up? Why do we care? Well, so there are two main applications or major applications of cycle integrals and their traces. One is in special values of L functions. So as soon as I say this, everyone should be thinking of Birch-Finit and Dyer, Bloch-Kato conjectures, all of these kind of things. The second one is towards arithmetic geometry, so in the green functions on Grassmannians. So cycle integrals, their traces describe lots of these green functions and certain values of them. They also appear in string theory, in loop amplitudes, in algebraic geometry. Basically, I'm trying to say that these cycle integrals that we'll see are everywhere. Okay, so some definitions. So where does our story start? It starts with Koenen and Zagier, who introduced these functions f, k sub b. Okay, and what are they? They're some constant times a sum of quadratic forms, and you just evaluate at some parameter z1 and take a power minus k. Okay, what's b here? So b is just some equivalence class of indefinite integral binary quadratic forms of some discriminant. So we fix some class of indefinite forms, and then we just sum over the quadratic forms in this class. And Koenen and Zagier studied this in the paper. And this turns out to be a weight 2k cusp form. So it's really a modular form. And they show that certain linear combinations of some cycle integrals over geodesics of these functions are rational. So this basically shows that there are some L functions whose special values are rational. Okay, so I've highlighted all the B's in orange. What does that mean? That means that we're going to do something to them. So what happens if we just change B? So what's the obvious change? I mentioned before that these were all indefinite. So what if we change them to positive definite? Okay, so let's make the same definition, but now I've changed B to a curly A, and A is just an equivalence class of positive definite binary quadratic forms, and I've changed D to little d just to show that there's a difference. Okay, then what are these functions? Well, now, because they're positive definite quadratic forms here, we have poles. So these are meromorphic modular forms. They're still of weight 2k, and they still decay nicely, but the point is now there are poles. So this is where these meromorphic modular forms come in my title of the talk. So it's really just the same functions here, just some sum over quadratic forms taken to a negative power, but now we take positive definite ones. Okay, so a little bit more notation. So everywhere I'll just call SL2Z as gamma. Okay, and I'll let this curly Q sub D denote the set of integral binary quadratic forms of some non-square discriminant. So just think of Q sub D as just all the binary quadratic forms you can think of. Okay, and a bit more scary notation. So C sub Q is some image in the quotient space of the upper half plane by gamma of some geodesic. Okay, what's this paragraph really saying? Saying, take your favorite quadratic form, ABC. Associated to that is some geodesic, which is just the set of points satisfying this equation. So A mod Z squared plus BX plus C is 0. So this is some geodesic in the upper half plane, some semicircle. And this small c is just the image of that when we quotient by gamma. So even though this looks a bit scary, this is really easy stuff. Okay, so what are we interested in? We're interested in the traces of some cycle integrals. So we define the trace. So this sum gives us the trace, and we just sum over all equivalence classes. So this is the set of all binary quadratic forms modded by gamma. And our cycle integral, we just hit fka with our quadratic form raised to the k minus 1, and we integrate over our closed geodesic here. And as I said before, these traces of cycle integrals show up in a lot of places. So for us, we're really concerned about the special values of L functions and rationality. And I'll keep touching on this theme of rationality as we go through the talk. Okay, so we work on lattices. So we want to restrict this talk to a nice lattice of signature 1, 2. In the paper, we deal with all signature 1, 2 lattices. So this means there's a positive definite part of 1 dimension and a negative definite part of 2 dimensions. And we fix this lattice L. So it just looks like matrices minus B minus C, A, B, all in Z. And there's some quadratic form with this lattice, which is just the determinant. Okay, why do we choose this particular lattice L? Well, we choose this because the dual lattice, I just called L prime, and we won't really see this much, but the dual lattice can be identified with all integrally binary quadratic forms. And then you just add in a -4 times Q of X to get to the discriminant. So we choose this lattice so that in the previous slide, we have a sum over quadratic forms. Well, we just choose this particular lattice to get back to this sum. But in general, we can choose any signature 1, 2 lattice, and the trace here will just change a little bit. We'll no longer sum over quadratic forms, we'll sum over quotients of lattices. Okay. And now I need to talk a little bit about the splitting of lattices. So I have this lattice L, a 1 dimension and a 2-dimensional negative definite space. And we kind of want to pull this apart into its components. But okay, so let's take a CM point in H associated to, basically associated to A, curly A. That just means I take some point in the upper half plane that's a solution of Q0, ZA1 equals 0. So this is just some quadratic equation, and I just choose a solution of it, the one that lies in the upper half plane. What does this do? This allows us to split this lattice. Okay, here I lie a little bit. This C sub A is not strictly the same as C sub A here. This C sub A that I'm talking about down here is the image in the Grassmannian. But because there's an explicit bijection between the upper half plane and the Grassmannian, I just call them the same thing. So we think of this C sub A at the bottom as just a line in our Grassmannian. So what do? We just intersect our lattice with this line and our lattice with the complement of this line. And it turns out that this positive definite lattice, P, which is L intersected with Z sub A, this line, is 1-dimensional and positive definite. And the same thing for N, but now it's 2-dimensional and negative definite. And the good thing is that P plus N has finite index in L. So we're not losing too much information by doing this. Okay. I also need a bit of notation on theta functions. So to a positive definite lattice P, in our case, we can associate a theta function. I'm sure everyone here knows how this goes. And it turns out this is a modular form of weight 1/2 with some Weil representation. Okay, ignore the representation stuff for now. We just think about this as some holomorphic modular form with particular weight. Okay, and by this curly GP plus in our talk, we'll denote the holomorphic part of a harmonic mass form GP that maps to theta P under our shadow operator, under psi. Okay, it's a bit confusing. All this means is choose curly G in the correct way such that under psi, I get theta P back. That's all I mean by this. Okay, so we just think of GP plus or GP as some special function that just maps to theta P. That's all we need. And finally, we have some weakly holomorphic modular form. So a weakly holomorphic modular form comes with some Q expansion with some coefficient CF of n, and here's basically Q to the n. And we fix this throughout the talk. It's of particular weight and satisfies some technical conditions on Kernan plus space conditions on this. Okay, but essentially it just says, choose your favorite weakly holomorphic modular form. What's the theorem? The theorem is take some even number, k, and assume that ZA does not lie on a geodesic, so these things are still defined, and that things are non-zero. Then I'll explain all this stuff on the right-hand side in a second. We have the sum of these traces hit with some coefficients is something to do with our modular form, our harmonic mass form, or the holomorphic part thereof, and some theta function. Okay, and what are all these extra things? CT, this just means take a constant term of some Fourier expansion. These Langle-Wrangle brackets are just a bilinear form on some group ring. These square brackets are the Rankine-Cohen brackets. So this just means a certain product of modular forms. And theta n, or theta n minus, sorry, is some holomorphic theta function, just associated to, now I change n to be positive definite. So it was negative definite before, so I just let the quadratic form be minus what it was before. Okay, so what does this mean? This means that some finite linear combination of the traces on the left-hand side is some constant term in some Fourier expansion. Well, up to some constant that I've left out here. Really, this is maybe a factor of pi or something different. Okay, so what's the point? Point is, all of these terms on the right-hand side, f, gp plus, and theta n minus, can be chosen to have rational coefficients. And then all I'm doing on this right-hand side is multiplying various things together, so everything stays rational. So anything that looks like the left-hand side is rational, or can be chosen to be rational. And then I should mention in the paper, we actually also prove this for odd K, generic signature 1, 2 lattices, everything like this. This is like the easy version of the theorem we prove. Okay, so now I'll talk a little bit about how we prove this and the more general analog. There are 3 main steps. So the first one, we look at the trace on the left-hand side, and we just identify it as the raising of a locally harmonic mass form, whatever this thing is. Okay. Second step, we take the output of step 1, and we relate that to a Siegel theta lift. And the third step is take the output of step 2, and we just compute it as the constant term that's on the right-hand side. So I'll skip most of the details of 1 and 2 and show a little bit of part 3. So for part 1, we want to realize this trace as some raising of something on the right-hand side. Okay, and this is basically already done by Schwarenscheid and Löblich. So the trace here on the left-hand side is up to some constant, the raising, or the iterated raising, of some curly f here. Okay, we can kind of ignore what curly f here, I said here. It's just some particular example of a locally harmonic mass form. Well, okay, so we have some object that we can write the trace as. How does this help? This helps because we can then show that this raising, this iterated raising of our locally harmonic mass form is basically actually a Siegel theta lift. And this thing is really well studied. Okay, so Siegel theta function, theta L we have here, and some raising of our modular form. And well, okay, there's some technical conditions on this, this integral here because we need to regularize it. Sometimes it doesn't converge. Okay, how do we prove this equality here? It's actually pretty straightforward. On the left-hand side, you just compute, see what it is, and as one might expect, you can do this by induction. And on the right-hand side, you just unfold a theta lift in the standard way. So you can follow Borchard's or Brunier's habilitation here and just unfold this integral and see what you get out. And just compare them, and then there's some hidden constant here as well that just fixes. Okay, so now we take the output of this, so this theta lift, and we can use Stokes' theorem and ideas from a recent paper of Brunier, Ale, and Yang, and just evaluate it as a constant term. So this is where the real magic happens, is in the evaluation of this theta lift as a constant term. So I'll talk a little bit more about how we do this. Okay, so first we want to shift this R operator from the left-hand side to the right-hand side. So from F, we want F to be alone. We want to shift our raising to the Siegel theta function. And this is easy. So there's just a property of R you can plug in here. And you pick up some factor of -1, but you're just allowed to switch R to the right-hand side. So what's the point? The point to use Stokes' theorem is we want some differential operator acting on theta L, but we want it in d by d tau bar. So we want like a lowering operator here, not a raising. So we've got to do something on this right-hand side. How do we deal with this? Okay, first, you can show that if you have some product, and remember that theta L, so the Siegel theta function splits into a positive definite, negative definite part. So you can show that there's a property of R, which means if you take a splitting of a function, g and h here, then I can just apply it to h. So that's exactly what we're going to do. We're going to split up theta L into positive definite and negative definite part and see what we get. Well, what do we get? We get exactly what I've written here. It looks a bit scary. Okay, so here, theta p plus m, so you can think of this as theta L. So here's our Siegel theta function, evaluated at Cm point, and I just put it apart. So here really is theta p. I've just snuck in my lowering of gp. So this is the image of gp is just theta p on this left-hand side. And the right-hand side, I have my theta n minus. So I've split my Siegel theta function into positive definite and negative definite parts. And luckily, here now I have my derivative that I wanted in the first place. So if I plug this into, well, a generalization of a proposition that was shown in Brunner, Ehl, and Yang, we can recognize this right-hand side thing as the lowering of some Rankine-Cohen bracket. So as some lowering of products of GP and theta n minus. And again, there's some hidden constants here. Okay, what does this all mean, all this technical business? Let's just plug that back into the definition of the theta integral. Okay, so the integral is now our integral over a fundamental domain. F is alone, which is what we wanted. L comes here, and I just stick in whatever this Rankine-Cohen bracket has to be. The point is now, here L is exactly the derivative we wanted. So now we can just use Stokes' theorem, and a super easy application proves the theorem in general. Okay, there's some technical things you need to do to show the vanishing of some boundary integrals from Stokes' theorem, but really this is the easy step, and the theorem's proved. Okay, in the abstract of the talk, I promised some examples. So let's choose some nice examples. So let's just choose a class of A, and let's choose it to be 101, so a super easy quadratic form. And let's choose a Cm point Ca equals I. Okay, then we choose, well, then theta p is exactly the Jacobi theta function. So a super nice function. Then we need a pre-image of this Jacobi theta function under our lowering operator. Well, Zagier showed that this could be chosen as GP plus here, which is basically the generating function of Hurwitz class numbers. Okay, so what does that mean? That means if we plug it into the theorem, we're going to get something to do with Hurwitz class numbers. Okay, so let's just choose a weight k equals 2 to start with, and we also get to choose f. So let's just choose it to be the unique weakly holomorphic modular form of this shape. So it begins e to the minus d tau plus O of 1. What's the output of our theorem? Our theorem says that the trace of the cycle integrals of this shape is some L value, LD of minus 1, plus a sum of Hurwitz class numbers. Recall that this is finite, so eventually this is going to be h of d minus something bigger than d, so this is going to be 0 eventually. So the trace is some, up to some L value, some finite sum of Hurwitz class numbers. You can play the same game for k equals 4. So for k equals 4, if we choose the same things, we again get some finite sum of Hurwitz class numbers, but with some extra linear factor here, or quadratic factor, sorry. And I also promised an example on some partition theoretic things. So if we let SPT be Andrew's SPT function, so this is counting number of smallest parts in integer partitions, and we modify it a little bit with the partition function we saw in Zach's talk. And here we have some Sn. So we take the smallest number of partitions of smallest parts, and something to do with P of n, then what do we get? We get some linear combination of traces this time, is again some L value, and some finite sum of S of n, plus some Legendre symbol. Okay, and for k equals 4, we get something a bit more complicated, but of a similar shape. So we get some rational number here, again Legendre symbol, again quadratic form here, and again some finite sum of S values, and some L value at the end. Okay, if you're interested, here's where the paper is available, and thank you very much for listening.
Great. Let's thank the speaker. Any questions?
I guess this was a little technical.
So I have a question. So you mentioned something very interesting in passing, or at least very interesting to me. So you said that there's an explicit bijection between the upper half plane and a Grassmannian, yes, which I guess is well known. Could you say what the bijection is?
Yes, so I think you basically choose, okay, so Z here is x plus iy. You just map it to some element in this lattice, and I think it's top left is x, and then x squared plus y squared minus x and y, something like this. I can look it up now, but there's an explicit description of you take x plus iy in the upper half plane, you map it to some line in this Grassmannian, just by mapping to some matrix, basically.
And I guess this preserves some kind of integral structure. Is that the point here?
Yeah.
Okay. Other questions? Okay. Let's thank our speaker again. So the next talks are in 7 minutes. So we have Alexander Clifton here, and we have Hester Graves in room 2.